In today's video, we're going to continue with comparing several means and looking at the ANOVA. We'll run the analysis in SPSS and we'll look at what we can do if we find that one or more of the differences between means is statistically significant. So let's start out by taking a look at our objectives again. And if you want to read these all, you can go ahead and pause the video at this time. Before we get into the ANOVA with SPSS, let's answer the question that I had in from a previous video in a previous class. Why do we have the alpha significance level for comparing two variances but not for an ANOVA? First, let's refresh on the F distribution characteristics. So there's a family of F distributions based on the numerator and the denominator of the F distribution. And the F distribution is continuous, it cannot be negative, and the F distribution is positively skewed. And although the image doesn't really appear to be that way, it is an asymptotic distribution, meaning these lines don't actually ever touch the x-axis. And you can see that as our degrees of freedom increase, it begins to look more and more like a normal curve. Now when we're comparing equal variant for doing the test for equal variances, we want to go ahead and cut the significance level in half. And we've chosen to do, and the reason for that is because we have chosen to place the larger variance in the numerator. So the observed F ratio, which is our computed test statistic, it'll never take a value of less than 1. And by putting the larger variance in the numerator, we've forced it into that situation where it'll never take a value of less than 1. And so what we're essentially doing is that we are looking at the right tail of the F distribution. We aren't looking at the left tail. So we remove half of the significance level that would be on that tail. On the other hand, when we calculate an ANOVA, we don't pre-select the larger variance to go in the numerator. We just evaluate both tails. We don't have the significance level. So let's get back to our ANOVA and let's do our example using SPSS. If you remember our example from a previous video, we had Brunner Marketing Research Company that was surveying passengers from recent flights. And it was a customer satisfaction survey among 4 different airlines: American, Delta, United, and US Airways. And we were tasked with the question of, is there a difference in the mean satisfaction level among the 4 airlines? We're to use the 0 or 0.01 significance level. And I'll give you a moment to read this. You can actually pause the video to read the full scenario if you'd like. Let's take a look at the steps that we do in SPSS. As usual, the first thing we want to do is set up our data. To do so, we go into our variable view and establish the variable names and the types, the labels, and the values in particular that's necessary for our grouping variable. And as I've stated in the past, you can name the grouping variable whatever it is that you want to name it, just as long as you remember that that is in fact the grouping variable. I tend to like to use the group name because it does make it easier to remember that that's the grouping variable. Now right away something should jump out at you when you look at the variable view that we have set up here. Remember the grouping view, our grouping variable here is labeled with these value labels. 1 equals American, 2 equals Delta, 3 equals United, 4 equals US Airways. And those are just based on the sequence that they are listed in the columns here. So what is not correct with what you see here? Well, the scale, or the measure, the level of measurement for our grouping variable is really just a nominal variable. So let's go ahead and fix that. And now we have it back to nominal the way it's supposed to be. Once we go ahead and enter all of our data elements into the data view, we'll see it look something similar to this. It should look exactly the same as this if you've chosen the same value labels as what I have placed in here. Now let's look at what steps we use to calculate the analysis of variance in SPSS. As in previous tests, I've provided the steps for you, or excuse me, as in previous videos, I've provided you the steps in SPSS in purple. So we go to Analyze, Compare Means, One-Way ANOVA, and that will pop up the One-Way ANOVA dialog box. Now, just as in other cases with SPSS, there's more than one way to calculate the result or the analysis that we're looking for. And for an ANOVA, we can go into the general linear model approach of SPSS also. We'll save that for another video though. So when we do Analyze, Compare Means, One-Way ANOVA, our One-Way ANOVA dialog box pops up, and we put our grouping variable into the Factor dialog box section, and then we put our dependent variable, which is our customer service scores, in the dependent list. For a simple one-way ANOVA, without doing any of the contrasts, or otherwise known as planned comparisons, or post hoc tests, we just select Options, and we select Descriptive and the Homogeneity of Variance test. If you remember from a previous video, this is actually the Levine's test of the homogeneity of variance. And what that's testing is, it's testing the null hypothesis that the variance in the groups are equal. We want this to be a fail to reject the outcome. We want a high p-value. In other words, the meaning behind that would be that we fail to reject the null that the variances are equal. If we reject the null, in other words, we have a low p-value, we have to switch our approach, and then we could do a Brown-Forsyth check or test, or a Welch's test, and that's beyond the scope of this video. If you read page 443 of our text, that'll give you an idea of which one is better based off of, well, the same answer that we use frequently. It depends. As for missing values, for our analysis right now, it's going to produce the same result whether we do exclude cases analysis by analysis or exclude cases list-wise, so we can leave the default setting here. Let's take a look at what our results are. So we get our descriptives table, and that comes from checking the descriptives block in our options of the one-way ANOVA. And there you can see the options or the descriptives for each of our different airlines. You have your N, your mean, standard deviation, standard error. So then we have our test of the homogeneity of variances, and the homogeneity of variances test is checked right here, and that is the Levine's test. Tests the null hypothesis that the variances in the group are equal, and in this case we have a significance level, or a p-value of 0.432, so the p-value is not low, so we fail to reject the null hypothesis here. And we can state that we fail to reject the null hypothesis that the variances in the group are equal. Now I've placed here the ANOVA output right above the ANOVA output table that we had from when we manually calculated out the ANOVA in our prior video. And I did put the wrong significance level here, so let me go ahead and fix that. If we look back at a prior slide here, the scenario provided us a alpha significance level of 0.01, and so now we have that correctly in here. So when we did the ANOVA in the other video, when we calculated it manually, we used an F critical value in order to determine our statistical significance. In other words, our decision was if the computed value of the computed value of our F test statistic that came from our one little sample of data was 8.99, which was greater than the F critical value of 5.09, so we rejected the null hypothesis. And we concluded that the population means are not equal. For today, we've got the SPSS output, and the SPSS output provides us the p-value in our sig column here. Now, one thing to note, this is not often that we get a p-value of exactly 0.001, and it's important to note this just for the sake of precision. When we get a significance or a p-value of 0.000, we report that as p is less than 0.000, or p is less than 0.001, excuse me. In this case, we have a p-value of exactly 0.001. So when we report this, we have to report it as p equals 0.001, and that'll differentiate between a p of 0.000 in our SPSS output. So you'll note here I've added these blue and red lines also because when you run the SPSS output, or the SPSS one-way ANOVA, it provides a different output term from what we were using in our other example. So SPSS breaks down the sums of squares into, or the sources of the variation into between groups, which is the same as the model sums of squares, and then within groups, which is our residuals sum of squares, excuse me. And you can see that our numbers are the same, they all match up, just the SPSS is out to one additional decimal place. But we have our 890.684, 890.68, 594.41, 594.407, and so on throughout the table. And again, we are provided with a p-value with the SPSS output. So our approach here, our decision rule, is going to be that if the p-value is low, the null must go. In other words, if the p-value is less than our chosen significance level, we are going to reject the null hypothesis that the population means are equal. Obviously, since we did this f-test the other day using the f-critical value in our manual calculation, we would expect that we would get the same significance when we do the p-value approach. And of course we do. The p-value of 0.001 is less than our alpha significance level of 0.01, so the null hypothesis is rejected. We conclude that the population means are not all equal. So that means that the mean scores are not the same for the 4 airlines. But the problem with this, and really not a problem, but a limitation of the analysis of variance table, is that it is an omnibus test. It is an overall test that only tells us that there is a difference in the group means, but we don't know where that difference lies. We don't know if it's a difference between American and US Airways, or Delta and United, or American and United, American Delta, and so on down the list. So then what do we do in that situation? We found that there is significance. There is a difference somewhere in the group means. What do we do next? There are 2 approaches that we can take after we find that the overall model is significant. We'll look at the post hoc tests today and planned contrasts perhaps in another video, but for right now we'll do an overview of the 2 different approaches. Again, these are what we do after we find overall significance, and there is a slight caveat on the planned contrasts when I say after. But for post hoc tests, and that's what we'll do today, we compare every pair of groups as though we're doing separate t-tests. And in actuality, we use stricter rules to ensure we keep our family-wise error rate at a chosen level of significance. In other words, in some ways, it's like we backtrack and we take our 0.01 level of significance that we have here, and we break that down so that we do our group comparisons of every possible group option, and we do that with a portion of that 0.05 family-wise error rate. And we'll get into a little bit more on that later, but suffice it to say that's a means that we can test our individual group means after we've gone ahead and tested our overall significance. We'll talk about a little bit about these 3 examples here today in this video. Before we do that, let's talk about the planned contrast. It's also called planned comparisons, and this is when you have a specific hypothesis or a specific theory on why or which groups are different from each other. And SPSS breaks down the variance into their separate components when we do the planned contrasts. Because you have the hypothesis on which groups differ, you should really input the contrast at the same time you run the ANOVA. So that's the caveat I was referring to when I said there's a caveat when we talk about after. If you know ahead of time that you want to test the hypothesis or the theory that group, I don't know, American is not equal to delta, then you should set up that contrast ahead of time. All right, let's take a look at the solution to the overall ANOVA once more. Now here you'll notice that in addition to the manually calculated ANOVA table that we did from the previous video and the SPSS calculation for the ANOVA table, I've also provided you with the ANOVA table with the breakdown of each of the individual calculations for each of the values within the ANOVA table as a point of reference. And again, we have our p-value of 0.01 is less than the alpha significance level of 0.01, so we reject the null hypothesis that the population means are all equal. Let's look at one of the post hoc tests. We'll start with the least significant difference method. When we reject the null hypothesis that the means are equal, we may want to know which treatment group means differ. One of the simplest procedures is through the use of confidence intervals, and the method we're going to use is, as I said, the least significant difference method. We use this approach after we've rejected the null that the population means are the same, and we want to know between which groups do the treatment means differ. We use a confidence interval based on the t-distribution to compare pairs of group means. If the confidence interval contains 0, we determine there is not a difference between the means. If you remember back to when we did the t-tests and we did the confidence interval, and we found that if the confidence interval spanned 0, then that means that there's a good probability that the population means are equal to 0. So here that same thought holds true. So here's our calculation for our confidence interval, and just like all of our other confidence intervals, we can look at it as an overview, and that is we take our point estimate, which is right here, add to it and subtract from it our margin of error. In this case, our margin of error is made up of our t value or our t critical value. In fact, let's write that critical value in right now. There we go. Now that's much better. We have our t critical value here times the standard error, and in this case the standard error is our mean square of the residual times 1 over our n sub 1 and plus 1 divided by our n sub 2. And this is where x bar sub 1, which we also can write as x bar sub 1, is the mean of the first sample group, and x bar sub 2 is the mean of the second sample group. We find our t value in the appendix A2, or we can use Excel Megastat to find our t value, our t critical value. Oh, and we have to change that too, it looks like. There we go. Now we have our t critical value in there. Our mean square residual is the mean square residual that we got from the ANOVA table right here. Oh, that's the degrees of freedom. Move over 1 right there. And n sub 1 is the number of observations in the first sample group, and n sub 2 is the second sample group. And backing up to the t critical value, our degrees of freedom is n minus k, which you'll notice is our degrees of freedom for our residual. And let's take a look at our confidence interval. So we're going to develop a 95% confidence interval for the difference in the mean between American and US airways, and that'll be based off of our original data set here. And the question we're asked is, can we conclude that there is a difference between the two airlines' ratings? So using the confidence interval formula that we had from the previous page, and oh yes, we got to enter the critical value in there, the CV, so let's do that. There we go. Now we have our T critical value in there, and we have our formula. And here I've changed the subscripts from 1 and 2 to A for American and US for US Airways, same as we've done in the prior video. Our X bar values come from our descriptives table, and or you could use our previous video. So if we look at our table here, we have the American mean is 87.25 and US Airways is 69. And then we have our T critical value. The T critical value is 2.101 from Appendix A2, with n minus k is the number as our degrees of freedom. In other words, that's the same as our degrees of freedom for the residual, n minus k, or our denominator degrees of freedom if we're looking at our F test statistic. But that goes back to our prior video. So our T critical value is 2.101. Remember, we have our point estimate plus and minus our margin of error. So we have our margin of error here. Mean square residual we can get from our previous slide right here, 3302. Here's 33. And then our n sub 1 and n sub 2, which I've also replaced as n sub a and n sub us. It's 4 and 6. When we run the calculations, 87.25 minus 69, we find it's 18.25, and then when we do the rest of the calculations here, it's 7.791. So our confidence interval ranges from 10.46 up to 26.04. So since the confidence interval does not include 0, we can conclude that these treatment means differ significantly. The 95% confidence interval, again, ranges between 10.46 and 26.04. And because we have the significance, another way that we can look at it is that the passengers on American rated service significantly different from those on United Airways. Well, how do you suppose we do this in SPSS? Well, let's take a look. We go back to our analysis steps, analyze, compare means, one-way ANOVA, and we have our one-way ANOVA dialog box. And we keep the same options as before. So we're keeping the descriptives and the homogeneity of variance, or Levine's test of homogeneity of variance. And now we go into the post hoc tests. And here we've selected a few of the post hoc tests. These are the ones that are recommended in our textbook, except there's a note for LSD, which we'll talk about later. We will use least significant difference test because that's what we used in our calculation right here, and we want to compare that to the output of SPSS. And these are what I recommend based on our book's text. And if you want to take a look on page 459, look at the summary section at the bottom of page 459 to take a look at and see what Andy Field recommends for these different tests. The Bonferroni test is a conservative test that keeps our family-wise error rate to the level that we selected of 0.05. And then Tukey's honestly significantly difference test, which is just labeled as Tukey here. Sometimes you'll see it referred to as Tukey's HSD, and that has good power and good control over the type 1 error rate. And power, we haven't really talked about a whole lot, but the power of a statistical test is the probability that it correctly rejects the null hypothesis when the null hypothesis is false. I'll say it again. Power is the probability that the statistical test correctly rejects the null hypothesis when the null hypothesis is false. If during our analysis we are not assuming that equal variances, then we would choose the Games-Howell test based on Andy Field's recommendation again on page 459 of the text. Once we've entered the values, we click Continue, we click OK, and we get to our results. And as I stated before, if we do the least significant difference test, it will provide the same result that we had in our calculation right here. So this was our 95% confidence interval, and the range that we had when we calculated it manually was from 10.46 to 26.04. Again, right here. And we get the same result from our 95% confidence interval from the least significant differences approach. Now if we look at Tukey, which is actually a better test than the LSD test, we can see that when we compare American against US Airways, we actually have a broader confidence interval, so we are more likely to hit 0 if we have this confidence interval here. Or in other words, we're more likely to span 0. And a good example of that is if we were to compare American to Delta using the least significant difference approach, we find that both of them are still positive. But if we look at the Tukey's honestly significantly different test, we find that we have a lower bound that's negative and a positive bound that is positive, which means that we cannot say that there's a statistical difference from 0 there. It's a possibility that the means are equal. And that's the basic confidence interval or post hoc test using SPSS. I hope you enjoyed this video. We'll see you at the next one.